So here we are with capacitors, which will be the penultimate topic in the advanced higher course. And we're going to start off with the things you're supposed to know already from the higher course. So what we've got here is a very simple RC circuit, which is the one you should be familiar with. We have got a DC supply, a switch, a resistor and a capacitor. And we're going to go through the items that we're supposed to know to make sure we can work with this kind of circuit before we go on to look at an AC circuit. The first two equations that we should know relevant to capacitors are these two. C equals Q over V, where Q is the charge stored on the capacitor. V is the potential difference across the capacitor. And C is the capacitance. And that's our definition of capacitance. The capacitance is the charge stored divided by the potential difference that's required to store that charge. So the charge, when we close the switch, is going to come around the circuit through the resistor, and negative charge is going to come here, and that means that electric repulsion will happen and negative charges from this plate will get repelled around to complete the circuit until there's no more energy available in the circuit, until all the work that this DC supply can do is holding charge on the capacitor. And that's going to have some important effects for the current, which you should already be familiar with. The other formula for the capacitance that you should know is this one. C equals epsilon A over D. And this is the equation that tells us how to work out the capacitance based on the physical properties of the capacitor. So A is the area of the capacitor plate overlap. Now in most capacitors that's just the area of the capacitor plates, but you can get variable capacitors which have the ability to move the plates so that they will change how much overlaps and therefore what the value of the capacitance is. These are quite rare in practice, but they do exist. D is the distance between the capacitor plates. C is, of course, the capacitance, again. And epsilon, well, you should already be used to the idea that epsilon is the permittivity, because you should be well and truly familiar with epsilon naught, the permittivity of free space. Epsilon R is the relative permittivity. Now, why on earth do we have a thing called the relative permittivity? That is because this gives us a value that allows for what material is between the two capacitor plates. If it's an air-filled capacitor, which is to say one where it's just air between the two capacitor plates, then epsilon R is so close to 1, we might as well just say that it is 1. In other words, we'd use the permittivity of free space. If, however, the capacitor was filled with, say, a plastic or a gel, or, believe it or not, paper is often used as a filler in a capacitor, like the meat in the sandwich, then we need to know how that is different from the value for free space. And we do that very easily by just going and looking up the relevant material in a data book. And what we will find is this epsilon R value. So for a given material, it may be the case that epsilon R is 1.4, in which case we multiply the permittivity of free space by 1.4, and that's the value we use when we're working out the capacitance. If you recall from your higher textbook, it said that the time constant was for interest only. It wasn't something that you were required to know. And at the time I said that was a bit of a fib, because it was a bit of a fib. And the issue is that, yeah, time constant is useful to know because they might have thrown it into the higher question paper, but we didn't actually say where it came from or what it was all about. And the answer to where does the time constant come from is the shape of the graphs for the charging and the discharging of the capacitors. So if we look at the charging graphs, and again remember this is all for a DC circuit, you'll be delighted to know when we do AC it'll be different. Then if we look at the voltage across the resistor against time, so time equals 0 on this graph will be the instant at which we close the switch. And if we look at the voltage across the capacitor in the same time frame, so again time equals 0 is the time, the instant we close the switch, what we find is that initially all the voltage available from the supply is across the resistor, driving as large a current as possible through the circuit. And as time goes on, that drops away, and we end up with asymptotes to both of the axes. Whereas the voltage across the capacitor initially is close to 0, is in fact 0 initially at the instant we close the switch, and then gradually builds up to a maximum value. And if we laid these two graphs on top of each other, what we'd find is that if you pick any point along the time axis, take the value of the capacitor voltage and the value of the resistance voltage, they would add up to give you the value of the supply voltage. So basically what's happening is the instant we close the switch, we have a high voltage across the resistor pushing a big current through the circuit. That starts to charge up the capacitor. Now as more and more charge gets stored on the capacitor, the circuit has to do more and more work holding that charge on the capacitor, keeping it there, which means that more and more of the voltage gradually ends up being across the capacitor and less and less and less ends up being across the resistor. Now what that means is that if we were looking at the current in the circuit over those same time frames, so yet again, time equals 0 on this graph is the instant we close the switch, what we'd find is that initially we have a high charging current which then drops away down like so. So here's where the time constant comes in. If we have the current being like so, then that's an exponential decay. So we're going to have equations that eventually have minus tau over RC appearing in them. If we look at the discharging graphs, then what we'll find is that if we have a fully charged capacitor and we allow it to discharge across some resistance or some like a bulb or something to make a flashlight, what we'll find is that the instant we start the discharging process, then it will start with a high voltage across the capacitor because it's starting fully charged, and then that will gradually drop down to be asymptotic to the time axis. The current, however, does something a little bit trickier, because what you have to remember, if the charge was put into the capacitor in one direction, then when we discharge the capacitor, it's going to come out in the opposite direction. So actually, my current discharging graph is going to look something like that. So, going from the top, we close the switch, the voltage initially starts across the resistor, gives us a high current. Voltage gradually moves across the capacitor to hold the charge in place, so the current drops down. That gives us a fully charged capacitor. When we then allow the capacitor to discharge by whatever means we do, the voltage gradually gets released as it's being used to do work to drive a current through the circuit, and the current will be coming out of the capacitor in the opposite direction that it went in. Now I've added two equations here, these two here, and they are equations that will tell us what the charge on the capacitor is at some point in time, the time being expressed in units of time constants, so tau over RC, exponential, Q max. One of these is for the charging of a capacitor, one of them is for the discharging of a capacitor. What I would like you to do is try to work out which one is which. Start with Q equals CV, and then look at the graphs. There's the graph for the charging voltage across a capacitor. There's the graph for the discharging voltage across a capacitor. From there and here, can you tell me which of these is for charging and which is for discharging? And the last item on the capacitors in the DC circuit that we should know about from higher is this page, which is from the Scholar Summary book. For those of you that have got that one, of course you've all got access to the Scholar Summary notes through Teams. And what I like about this table is it is the neatest summary of how capacitors work in the DC circuit that I have ever seen anywhere. So for example, if we look at the charging section, at any instant in time, the supply voltage is equal to the voltage across the capacitor plus the voltage across the resistor. The current in the circuit is equal to the voltage across the resistor divided by the resistance. Starts discharge, so VC equals 0. Ends up fully charged, so VC equals VS, S for supply. At the start, the voltage across the resistor is equal to the supply voltage. Voltage across the capacitor. Sorry, at the end, the voltage across the resistor ends up being 0. At the start, current in the circuit, Vs over R. Fully charged capacitor, current equals 0. And then for discharging, voltage across capacitance equals the voltage that's available to be the supply. Because remember, when we're discharging it, we have disconnected from the DC supply that we used to charge the capacitor in the first place. So initially, the voltage across the capacitor is the supply voltage because we've replaced the supply voltage with whatever voltage we've put in the capacitor, put across the capacitor rather. And when we fully discharge the capacitor, we end up with 0 volts across it. They've all gone, they've all been used to drive a current through the circuit. And here's this current through the circuit. So at any point in time, the voltage across the resistor, in this case it'd be the load resistance, that'd be maybe a bulb or some sort of device we want to run with the capacitor, or if you're just determined to do something silly, perhaps a bit of wire that you're trying to melt with the capacitor. And there we go. So initially, voltage across whatever it is we're going to use as our load equals the supply voltage. But remember, the supply voltage is the capacitor voltage when we start to discharge something. Voltage across the resistance ends up being 0 when we're finished. Current, Vs over R to begin with, 0 to end up with. So capacitors, whether we're charging them or discharging them, the current ends up being 0. Whether we are charging them or discharging them, the initial current is the supply voltage over the resistance in the circuit. When we charge a capacitor, Vc is 0 and ends up equaling the supply. When we discharge a capacitor, the voltage across the capacitor starts as the supply because it is the supply and ends up being 0. There you go.